Hey kids, Smath here. No, but Arville's definitely not here. So, well, I'm here. Happy Friday. Oh, wait. No, it's Monday. Recording this on Friday. Happy St. Patty's. Anyway, hopefully you just watched the video on Doppler shifting. Today's lesson's about the apparent change of a frequency due to the relative motion between a source or observer. Got to know that for the test. A Doppler shift is the apparent change in the frequency of a wave due to the relative motion between the source and observer. In SB 2023, we can Doppler shift a lot of waves. If I went to the beach and stood in the water and let a wave hit me, and then I waited 1001, 1002, 1003, and another wave comes by, that is the period, say 3 seconds or 4 seconds. The frequency would be the inverse of that. So if it took 4 seconds, 1001, 1002, 1003, 1004, 4 seconds for a wave, that's the period, the frequency would be 1/4 or 0.25, a quarter wave per second, 0.25 hertz. I can alter that frequency. I can experience a different frequency by moving through the waves or with the waves. Maybe the waves sped up and we're moving towards me faster. Here's an example. We've all seen the little kid on the beach who gets out, is so excited, drops all their stuff on the beach and just goes flying through the waves. Boom, 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 boom. They fall down. They get up and they run back to the beach, turn around, boom, 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 and fall down. That child didn't experience the same period of 4 seconds or the same frequency of 0.25. Their period was much shorter. The frequency was higher. They experienced a frequency more like boom, 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 not 1001, 1002, 1003, 1004. So their period and frequency have been changed. They've been altered. They've been Doppler shifted. This is how you get pulled over with a radar gun. If I send a radio wave out to a car that's not moving, the radio wave hits the car, comes back, it's in its same state. It returned kind of like a mirror image of the first wave, same frequency, same wavelength. But what if that car is rushing towards me? As that car is rushing towards me, the wave I send out gets Doppler shifted. It gets sent back with a slightly higher frequency. That higher frequency means that that thing is moving towards me, or maybe I'm moving towards it. This is how we do radar for weather. We send out radio waves. If there's nothing there, the wave's gone forever. If there are clouds there that aren't moving, they return in their original state. If the storm is moving towards me, the waves come back Doppler shifted, meaning they have a higher frequency. If they're moving away from me, they have a Doppler shift in the other way, a red shift, a lower frequency. The faster the clouds are moving, the bigger the shift. So here's your actual equation. You just saw that in the video, but here's the equation. The altered frequency is F prime. That's the frequency I hear, the observed frequency. The actual frequency is F. So I'll just put this all on the screen for just a second. V here in red now is going to be the speed of sound in air, 343. VO is my velocity of my observer. VS is the velocity of the source. We're going to do 3 examples. This will help you with your homework today. There's a couple things to note though. If the observer is moving towards the source, we call that positive V. See, the equation is V plus V0, V observer, over V minus V source. But it's a little bit tricky because if the source is moving away or towards, that's going to be negative or positive. I still leave this minus sign in the equation. So this stays. But the question is my VS positive or negative? If it's negative, then I'm actually going to add that term on the bottom. Or up top, is my V observer positive or negative? And again, you'll see these in the examples in a minute. But for now, if something is moving towards, it's going to be positive. If something's moving away, it's negative. You leave these positive and negative over here. But if my source is moving towards me, I'm going to make that positive. If my source is moving away from me, it's going to be minus a negative. Does that kind of make sense? So here, I'll leave this on the screen for just a second, or you can pause the video. You can pause it at this point if you need to write this down. Let's go ahead and do our 3 examples. First example, very simple. An observer drives at a speed of 40 meters per second towards a stationary source. So you got a siren that's just making a noise, 400 hertz. What do I perceive? Now, because I'm moving towards the source, I expect a higher frequency. Let's see how much. The way the equation works out is my observed frequency is going to be V naught, so that, or not V naught, 343, that's the speed of sound, plus, because that 40 is moving towards, it's a positive 40. So that goes in there just like this, over 343, but the source isn't moving. So minus 0, or just 343 plus 40 over 343. My frequency is 400. So again, this is F prime equals V plus V observer over V minus V source times the original F. You can see what I'm going to get is 383 over 343. And that's why that frequency is going to go up. It's going to be greater than 1 for that term. Oh, and there's my answer. 446. When you get pulled over, the radar gun is determining by the Doppler shift of the wave exactly how fast you're moving. We can work it backwards to figure out how fast the source or observer is moving when that wave is Doppler shifted. It's the perceived change in pitch or frequency. Pitch for sound between the wave, excuse me, the source and the observer. My second example. Again, I'm going to go through this kind of quick, but you're welcome to pause. Oh, the answer's down there. An observer is at rest while an ambulance emitting a frequency of 550 hertz drives away from the observer. So now here I am standing, and there goes the ambulance. I expect lower as that the ambulance moves away, lower. Well, how much lower? 468 from 550. How did we get that? The observed frequency is going to be 343. Well, this time I'm not moving. So plus 0, or just 343 over, but I got to leave that 343 there. That's important. Over 343 minus. Now this is a little bit tricky. The source is moving away from me. Away means negative. So minus a negative. That's why that term is getting bigger down there. Going to drop my frequency. Minus 60. So minus a negative 60. That's why that ends up being plus. Now I'm going to multiply that all by 550. So the math would be F prime is equal to 343 over 403 times 550. And that's where my frequency is going down. Make sense? Really not too bad today. Doppler shifting. The worksheet shouldn't take you too long. You've seen the video. Definitely know that term for the perceived change in pitch or frequency due to relative motion. It's a great multiple choice question. And here's the last one. You can see the answer down there. I'm going to show you the math. Oops, an observer moves at a speed of 30 meters per second towards the source that is moving 70 meters per second toward the observer. They're both moving toward each other. I expect higher. It's going to be a higher pitch. If the source is emitting a frequency of 300 hertz, what is the frequency heard by the observer? Okay, so once again, F prime is equal to V 343. Since the observer is coming towards me, that's a positive, it's plus positive 30 over 343 minus the source is coming towards me, towards is positive. So I'm going to leave that number as positive 70. It's still minus in the equation times 300. One thing that helps, I think, with Doppler shifting is predicting. It gets a little bit tricky if one thing is moving away while the other thing is moving towards. Like if I'm speeding away from a police car that's approaching me, well, it's going down because I'm moving away from it, but it's going up because it's moving towards me. So it gets a little bit tricky. Predict something though. For this one, I expect a pretty big shift because I'm moving towards it and it's moving towards me. If only one thing is moving, it's pretty easy to predict. If it's moving away from you or you moving away from it, the frequency's got to be lower. Back to the kid at the beach. When they ran through the waves, boom, 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 boom. When they turn around and run back towards the shore, it's like taking forever to get to the next wave. In fact, you could run in such a way that the waves like stop relative to you. And that's again, Doppler shifting. You haven't changed the actual frequency of the wave, but you've changed what you're perceiving as you move into or away from those waves. Once you do this, I should get a pretty big shift from 300. I get 409.9. That should be enough to help you with the homework. You might have a situation where you have to solve for a velocity. So if you're solving for velocity and you know the observed frequency, say the actual frequency is 300, but the observed frequency is 340. How fast is the observer moving? Then I could do 343 plus V naught. And as long as the source isn't moving, I would just have 343 down here. But there are different ways to solve this in case you have to solve for a different variable. Make sense? All right. That's the lesson for today. I will see you guys back on day 2. Take care. God bless. Check them. Check them. Check them. Check them. Check them. Let me know STEM.